started when me and my friend were having coffee and we were talking about football. And while speaking of football, we started speaking about Beckham and what he's been up to. And basically, Beckham is known for the phrase "bend it like Beckham," and that essentially means that when he takes a free kick, he puts a slight spin on the ball, and the general spin on the ball changes the trajectory of the ball in that general direction. So it doesn't go straight, It has a slight curve to it. Most of you will know it anyway. So this essentially confuses the keeper, and if there's a wall while he's taking a free kick, then he can sidestep the wall. So if here is a wall and he's taking a free kick, and here's the goal, he can essentially curve around the wall and into the goal. That's the point of this. Now some players also have a different kind of spin they put on the opposite direction, and the ball curves in the opposite path. Its trajectory is just the opposite. And now we talk about another player, Ronaldo, and he does something slightly different. What he does is he doesn't put a spin on the ball which is horizontal. He puts it perpendicular, so it's a vertical spin, or what is known as a top spin. If many of you play tennis, you know what I'm talking about. The spin is essentially in this direction. So it's like that, if you can picture what I'm saying. So he rolls the ball in this way. Now what that essentially does is that once he kicks the ball goes on to its trajectory, but then suddenly comes down. So it just there's suddenness involved in that motion. And so what that does is that it goes over the wall. It goes over the wall of men during a free kick, and the goalkeeper suddenly thinks that the ball is going to go above the goalpost, but then it suddenly just drops down at the last moment. So essentially that means that another spin on the ball, a different kind of spin on the ball, has another changed trajectory. Now he puts a top spin on the ball, so you can see the direction of the arrows. That means this way. So we were thinking about, what if there was a player and he put the opposite spin on the ball, a back spin? What would happen then? So there were two scenarios that we concluded could happen. Number one was that the ball would go up, and while it was coming down, it would suddenly go up again and then come down later. Another possibility was that the ball would just stay prolonged in its motion for a very long period of time. It would take a long time till it comes down. Now we both don't know that much of football, but I mean, we like cricket more. But anyway, this was what we were discussing, and I said that why aren't these two things possible? These two scenarios seem to be very possible. They're just the opposite of what this guy does right here. But my friend was, no, there's something called gravity, and nothing can beat gravity. The ball just can't do this and go up and defy gravity, or just stay prolonged in the air for a long period of time. So what he was trying to say was, in short, that whatever causes this spin and change in trajectory cannot overcome the power of gravity. And that is what I want to discuss today, and hopefully prove my friend wrong. That's the point. So I researched a bit, and there's something called the Magnus effect that basically causes the ball to change its trajectory, and this is what I'll be introducing you to today. Though before we speak of the Magnus effect, we need to speak about the Bernoulli's principle, which is basically the backbone of the Magnus effect. Now, the Bernoulli's principle has got something to do with pressure and velocity, the relationship between these two. It's quite interesting. So what happens is, okay, so here I've got two pipes, as you can see. The first pipe has a big diameter first, and then a constriction, and then a smaller diameter. Second pipe is uniform throughout. Now, listen to me carefully. If we have water flowing through these pipes, there's water going through these pipes, and there's a bucket. Now, I want to imagine that both these pipes are connected to a pump. Okay? There's a pump here which is supplying an equal amount of force. Now, you can try this at home as well. I'm sorry I don't have the equipment myself, but you can try it if you have got it anytime. That if I have the same pump, and if I've got these two different pipes, the amount of water filled, the level of water filled in the same amount of time will be exactly the same. That means the rate of volume flowing will be the same. Now, but this leads to an interesting conclusion here, that in the second part of the first pipe and the first part of the first pipe, there will be a difference in the velocity of the water particles, because now there is a lesser diameter over here compared to here. So each particle will have to be faster in order to create more space so that more water can come in and fulfill the exact same amount of volume as in the second pipe. So this means that in region 2, the velocity of the particles is more than in region 1. And what this essentially means is that the kinetic energy in the second part or held by the water particles is much more than the kinetic energy held in the first part, which is a contradiction to the conservation of energy. So how is this problem solved? Well, there's quite a simple solution to it actually, because if we, on further inspection, we can see that kinetic energy is not the only kind of energy that is held by by this stream of water. There are two other forces. So the two other forces are, first, so I'm talking about the first area. It is the energy held by the pressure of these particles within, plus, yes, the kinetic energy. So that will be half mv1 square plus the potential energy, that means the distance from the ground needs to be taken into consideration, plus u1. Now this has to be equal to the amount of energy in the second region, so that will be P2 plus half mv2 square plus u2. Now U is potential energy, and I'm pretty sure that all of you know what that is, because I'm not really going to explain that. And I just want to explain what P1 and P2 are essentially. So I hope all of you, I mean, if you know Pascal's law, this will be simple for you. So that basically means that the amount of pressure that each particle puts on the other particle, the amount of energy that is basically a result of this, that's what P1 embodies in short. Now you might be thinking that is this the same pressure as the one that hits you? You know, hits the water that when it comes out. No, these two pressures are not the same. This pressure P1, P2 are a sort of internal pressure within the water itself, and this, what I like to call external pressure, is actually the pressure of the water hitting you when it comes out. You know, so Pi is basically the pressure within what these molecules hit each other with, and Pe is something what the pressure of the water will be hitting into the bucket, which is an external body. So P1 and P2 are not equal to the pressure that the water will be hitting the bucket with. I hope this is clear. Now, so we are essentially saying that V2 is greater than V1, and we also know that the potential energy have to be equal, because they're both on the same level almost. So we can just write this out. Now, to conserve energy, such that LHS has to be equal to RHS, we can say that P1 has to be greater than P2, right? That essentially means that when velocity is greater, then the energy due to pressure, internal pressure, is lesser, and vice versa. Now, this might seem slightly counterintuitive, because like I said, over here, if the water were to come out onto the bucket and you were supposed to measure the pressure, okay, then you'd say, you can easily say that PE1 will be greater than PE2, okay, first pipe, second pipe. That is absolutely correct. However, like I explained earlier, PE is not equal to PI. This relationship does not hold true. These are two different kinds of pressures that I'm talking about. This is essentially what Bernoulli's principle is all about. And from now on, we'll be discussing this. We'll be discussing the Magnus effect thanks to this beautiful thing right here. This is used in a lot of things, by the way. It's good to know about this. Okay, so let's get on to the Magnus effect. Right. So I've got this football here, and I want you to imagine that it's flowing, it's going through air, okay? It's cutting through air. So there's air over here, okay? Now what's going to happen essentially is, and I want you to imagine that there's a spin to the ball, okay? There's a spin in this direction. And this spin is vertical, okay? It's a back spin. If you can imagine what I'm talking about. So it's a back spin, okay? There's a back spin here. Now, so the air particles will come, and they will be thrown off because of the ball, you know, it's a body. They can't just simply go through the ball, so they'll have to go through the sides. And these particles will be, you know, and once they get onto the sides, they'll have to come to the back end again to fill in the vacuum created over here. So then they come back, yeah? In the same direction, the same thing will happen. The air particle will come and try to fill in the vacuum again. Now, I'm going to call this region region 1. This is region 2. Now, if you see carefully, the velocity in region... Okay, another thing. Let's say that this ball's angular velocity is omega. And the speed of the air or the ball, it depends. And let's say the speed of the translated speed of the air of the ball is v, which can also be seen to be the speed of the air hitting the ball. It depends on which perspective you're taking it to be. So in the first region, the total velocity would be first region. As you can see, there's an amount of friction between the ball's surface and the air. So what essentially is happening is that the air is moving at a speed v, but omega is being added to it because it's being flicked further by the ball. You know, this air particle is coming into contact with the ball and is being flicked in the same direction. So the air particles in region 1, the total velocity is v plus omega. And in the second region, the exact opposite is happening. The ball particle here is hitting the air in the opposite direction. Okay, so it's trying to stop it due to friction. So the amount of velocity in the second region held by the air particles is v minus omega. Now, remember what we talked about in the last slide about Bernoulli's principle? So we can say that v1, the velocity by the air particles in the first region, is greater than v2. And remembering Bernoulli's principle, we can then say that p1 is lesser than p2. That essentially means that there's more pressure here in the second region and less pressure in the first region. So what happens when there's a pressure difference? Nature always balances, right? So there'll be an upward force on this ball. This is what the basic theory is when I was telling my friend that if you put a backspin on the ball should be going up. So now the entire question is whether this force, this upward force created by the Magnus effect, can be greater than the force created by gravity on the ball. That's what the question boils down to. So what is the formula for the Magnus force by the Magnus effect? Formula is Fm is equal to S into V into omega. Now I've already mentioned all three variables somewhere or the other while I was explaining this. Now what is S? S is the air resistance coefficient. Air resistance coefficient. By the way, I hope my spellings are correct. I'm not very good with that. Anyway, so the air resistance coefficient, basically the air resistance coefficient specifically between the ball particles and the air particles. Okay, so it can change from ball to ball. The second thing is circular velocity. That's what omega is of the ball. What is V? V is the velocity of the ball or of the fluid, depending on which perspective you want to see it from. So this is what the Magnus effect is all about. Yeah? Okay. Moving on. So now, I will need to introduce a relationship between torque and angular acceleration if I am to solve this problem. Now what essentially is happening is that when I've got a ball and some player kicks the ball and he's putting a certain spin on it, okay? So this is the center of the ball. And so what exactly is happening is that he's going to hit the ball at somewhere at the bottom of the ball, okay, here somewhere. And the force is going to travel inside the ball, and that's going to create a spin. So what's happening here is that it creates a torque on the ball. Now, let's say that the force that is going into the spin of the ball is called Fs, okay? Okay, and the distance between this force and the center of the ball is r. So the torque would be equal to Fs into r. Yeah. Now, a simple mathematical, step, ma into r, so that means torque, is equal to mv into r into t. Now I want you guys to understand that when somebody is taking a free kick, your u is equal to 0, your initial velocity. And what is acceleration? Acceleration is v minus u upon t. Now my u is equal to 0. So I can easily say my acceleration is equal to the final velocity upon t. That's exactly what I've done here. Okay? So now I can say that torque is equal to m omega r squared into t. I want you to remember that v is equal to omega r. That's all that I've done here. Okay. So I hope you guys understand what I'm trying to do. What I'm essentially trying to do is, I'm trying to find a relationship between a guy hitting the football and how that translates into rotary motion, into its spinning, and how we can assess the magnitude of its amount of spinning by getting the amount of torque, because that's where the thing lies. So now, anything familiar here? Now mr squared is equal to the inertia of moment. So we finally get the inertia of moment into omega upon t. And now what we want from here is omega. Because if you remember that Fm is equal to S into V into omega. It's very simple to find out V, very simple to find out S. We need to find out omega. And now omega is equal to torque into T upon I. Now let's understand this quite well, what we've done here. Oh, sorry about that. Okay, what we've done here essentially is that we've understood the amount of force being applied by the person taking the kick on the ball, and we can easily find out the radius r of the ball, and from this we can calculate the angular velocity that the ball will finally have by using this formula. That is the beauty of this. That is the beauty of this, this relationship between the torque and the angular acceleration. So essentially, we've transformed a linear force into a variable that basically describes the circular motion of the ball. That is at the very heart of this concept. By using this formula, we're going to use this further. Okay, now a lot of you may not know what this is. I just randomly took m and r square and put I there. So what is this I? I just want to have a slight digression from this video into the inertia of moment. That's what that formula was all about. So basically I said that I is equal to mr square. So what is the inertia of moment? It's quite simple actually. So I've got two masses here, okay? Two bodies. So this is a smaller mass, this is a bigger mass. And what does inertia mean? Inertia just means that to move this mass forward, I need a particular amount of force, right? But for a bigger mass, I'll simply need a bigger force, right? That is normal linear inertia. Now, what if I've got two objects and I want to rotate them? I've got a smaller object with a lesser mass. I'll need a lesser force to rotate this object. Now, if I've got a bigger object, I'll simply need much more force to rotate it, right? So what I'm essentially trying to do here is, I'm trying to say that inertia of moment is basically inertia, but for a circular motion. It is the equivalent of inertia for a circular motion as compared to linear motion here. So, now the two things that affect this inertia of circular motion are the one, obviously the mass of the object as it is in linear motion, and the added factor is the placement of the mass around the center of rotation or the axis of rotation. Now, obviously that's quite obvious because torque increases with the distance from the center of the mass. So more the distance I have, the wider the disk I have, the tougher it will be to rotate the disk. It's as simple as that. Okay, so now I want to derive the formula. So inertia for linear motion, normal linear motion, the amount of energy can be called as half mv square, right? Now I want to convert this energy required to put the body into motion for a circular motion. So V is equal to omega r, as you all know. That will be half m omega r squared. Now, as you can see over here, in these two equations, half m is the same. Sorry, half. Yeah,